Vinamra Agarwal, who has also recently completed his third year. So he's in his fourth year, I guess, at this stage.
Yeah. Just one second. So how is this? Oh, wait, what happened? Hang on. Let's see. Yeah. So is this okay?
We see it well, and Vinamra is going to be speaking about his mechanics and materials laboratory, and this morning I mentioned you're doing atomistic simulations, but he's also doing experiments. So he's one of the rare people that tries to really do everything with respect to the gamut. So Vinamra, I'll let you tell them more about that.
Sure. Okay. So before I start, I just want to say I'm a person who stutters or stammers. So if you don't understand something, please ask me. I'll be happy to repeat it. So today I'll provide a brief overview of all the things going on in my lab, and we'll just focus on a few topics. So let me start by giving you a brief overview. So our goal of this lab or the research in my lab is to understand mechanics of materials. We primarily focus on computations, but we also use some experiments to try and understand material behavior at different length scales. So one of the first things we look at is towards impact cratering processes in planets. Impact craters is extremely useful as a landing sites for rovers, and impact craters also tell us a lot about planetary evolution. So we are doing some field observations. We are doing some simulations to understand craters. The next thing we'll look at is towards damage mechanics, where we try to understand the damage at the micro scale and use that information to develop damage laws at the macro scale. We are looking into fiber reinforced polymer composites, and we also are interested in metals. A lot of my work is towards nano and mesoscale mechanics, where we look at individual atoms. We'll look at grain boundaries, and we try to predict what will happen at the macro scale using information at the lower length scale. We also do some experiments. So what you are seeing here is a picture of a split Hopkinson bar, which is designed, calibrated, built exclusively by undergraduate students. And using this, we are subjecting 3D printed metals to a dynamic compression, and we are trying to predict its stress strain response, trying to obtain what would be the contribution of the microstructure in its overall stress strain response. And lastly, a new exciting adventure that we are doing is machine learning. Basically, the idea is, can we accelerate all this? Can we augment our equations? Can we augment our simulations with machine learning, and can we try to speed it up? So we'll talk about it in detail in the next few slides. So this was a brief overview of all the research in my lab. Let me first dive deep into multi-scale mechanics and design. What we are trying to focus on is a high strain rate loading scenario. Essentially, impacts. So impacts are extremely common in aerospace and defense industries, and our goal is to be able to design materials whose response can be, which have a better damage resistance in these kinds of scenarios. To be able to do that, we need to understand what happens at all these different length scales, and then we can talk about, can we use the information from lower length scales to design a better material. Okay? So if I look at different length scales, if I try to identify what happens in a shock loading, in an impact loading, at the lowest length scale, at the atomistic length scale, you see some defects, you see voids, dislocations, atoms will slip. You'll see all these defects starting to generate at the lowest length scale. Then at the grain length scale, you'll start to see crushing, you'll start to see grains being rotated, sliding, all those things. And then at the macroscopic length scale, you'll see failure and fragmentation. You'll start to see things break, you'll have an ejecta, you'll have all these things going on at the macroscopic length scale. So our objective is to try and understand these things at multiple length scales. But of course, there are problems associated with each. So if I look at atomistics, it's extremely challenging to do it's extremely challenging to do simulations with billions of atoms. It becomes computationally intensive, and it would take years and years to do an actual simulation containing hundreds of billions of atoms. So you can try to do some simulations at the grain scale. The issue with that is it requires extensive calibration. You need to know what are the grain orientations. You need to have a list of parameters you need to be able to represent the subgrain information. And then you lose that information. You can't get all these defects exactly. And then at the macro scale, the issue is everything gets homogenized. So you see a very average response. It's very hard to identify which microstructural information is useful. If I want to change a manufacturing process, then which microstructural features should I be targeting? All that information is lost. So are the broad question we are trying to ask is, can we somehow understand these large scale process using atomistics without sacrificing any details? Can we do that, and can we do that in an efficient way? And then can we use all this information and actually try to design a material from the ground up? Okay? So let me start with an example. So let's say you have a material and you're zooming in and you see all these grains in there. If you have a shock that is propagating through, of course it will lead to some defects. Okay? And our goal is to bring in atomistic information in this scenario. So what we are doing is we are developing a novel framework that gives you the best of both worlds. It tries to model this problem using atomistics and to still not compromise on performance. Okay? So the way we do this is we define a region of interest. We have a shock wave. That shock wave is a region of interest, and within that region of interest, I have all the atomistic information I need. And as the shock wave is moving, this region of interest is moving. So we don't need in atomistic information beyond this region of interest. So beyond it, I can have continuum equations. Okay? And finally, we can do this information communication cleverly. So if I boil this down into one picture, it's this. You have a region of interest, which is denoted by this purple box. Inside this region of interest, you have atoms. The information is represented through atoms. And beyond this box, you have continuum. This Herc is being actively pursued through a recent NSF grant, and we are actively publishing on this, and hopefully we'll have a full scale framework in place soon. The next thing we want to do is we want to take this information that we obtained at the grain scale and try to bring that over to the macro scale. With collaborating with external researchers, we are trying to model grains, grain boundaries, and cracks, and we are studying the interaction of cracks with these grain boundaries, seeing what kind of grains are resistant to crack nucleation, what kind of grains are the cracks can go easily through them, and we are trying to understand the failure mechanism using. The materials of interest are new cutting edge materials like nanocrystalline materials and 3D printed metals and alloys. So this work is being actively pursued. The next thing I want to talk about is machine learning. So let me again start out with an example. So let's say you have some material system, let's say 3D printed steel, and you're trying to look at the failure process of that. So you zoom in and you see all these grains, you apply some loading, the grains start to deform, and you have a crack that starts to form, and you want to model this extremely complicated process. So you start with material system, in this case 3D printed steel. You develop a model depending on what length scale you want. You try to do some very high fidelity simulations that can take into account all the things that are going on. You do extensive validation through experiments, and then hopefully, if everything goes well, you have a digital twin. Of course, there are certain details involved in this high fidelity emulation, and these are all the details. It's not done yet because you also need an extensive list of parameters you need. You need some constants for elastic behavior, some constants for plastic behavior, damage behavior. You need all the information associated with the microstructure, like grain orientation, grain boundaries, all of these things. And as you can see, this becomes extremely complicated. So you may start to think, well, how much time does it need? And the answer is it depends. It depends on what you are trying to simulate and how much details you need. And often these kinds of simulation can take hours, if not days. So our goal is, can we use machine learning to accelerate this process? And we don't want to compromise on the physics of the problem. We want to leverage the state-of-the-art architectures, and we want to be able to, we don't want results that would be inconsistent from physics. And then we can ask, how much speed up do we get? Okay. So let's start with an easy problem where we are just detecting microstructural features like pores, particles, and grain boundaries. And it turns out it works fairly well. If I give it a quick picture of a microstructure, I ask it to identify all the pores. It gives me the location of the pores. It gives me the aspect ratios, all this information. If I give it an input of this picture and ask it to identify all the grains in there, it can give me the information about grains, and you can keep extending it. The point is, it can do all this. It can cut down your feature identification from hours to minutes. Okay, so he can try to do a slightly more complicated problem of crack propagation. Can we look at all these cracks in the microstructure and try to predict how these cracks will grow and coalesce? And it turns out it works again fairly well. On the left, you are seeing the simulation through XFEM. On the right, you are seeing a machine learning prediction, and you can see there's like exact match. So we are actively pursuing it. We are working on it, and stay tuned for some exciting results in the future. So that, I thank you all. These are my students. There are plenty more collaborators, and we are grateful for the funding that's supported this work. Thank you.
Thank you, Vinamra. It's nice to see this every time because you just see those steps forward. And I hadn't seen the machine learning stuff at all. So
yeah, it's new. It's new.
Any questions out there? I know we've warned people out. It's coming on lunchtime.
It's lunchtime. I understand.
I'll ask a quick question though on the machine learning. What kind of computational time are you seeing on that compared to some of your other stuff?
So I mean, this cracks emulation, the simulation on the left took an hour. The machine learning prediction took seconds. So it's a huge speed up. It becomes especially important when you're trying to detect any of these, like in the previous case when we were trying to detect pores and stuff, usually the algorithms involved are quite expensive and they can take hours to do all this. He can do it in seconds or worst case minutes.
So is machine learning going to be pretty much the new basis for analyzing materials, since it seems to have a practical side and a fairly fast side to do the analysis?
So the key question is, we don't want to replace the mechanics, because machine learning is just it's not based on equations of mechanics. So you don't want to compromise on the physics of the problem. So in some ways, the future I see is machine learning will help augment the mechanics. It will help speed it up, but it won't like replace it.
All right. Well, I think that is the time for our session. Thank you again to Vinamra, Russell, and Suhasini. And definitely please reach out to them if you have other questions, and we'll be posting things online. Otherwise, everyone enjoy your lunch. And for those that are coming back, we start back up again at 1. So thank you.